At this point, we'll now go ahead and open up MATLAB and learn a couple of commands that are helpful for frequency response analysis. So we'll go ahead and first define our Laplace variable. Then we'll create a transfer function. And this system that we're creating is one that we looked at when we were studying the root locus, if you recall. So there we've created a transfer function. We can create the Bode plot using the command Bode. We get that Bode diagram. You can see a couple things. One, our system, our open loop transfer function, had a pure integrator, so you can see the slope is negative 20 dBs per decade as omega approaches 0. You can see that the phase is minus 90 degrees at low frequencies, also because of the integrator. At high frequencies, it drops down an extra 180 degrees, indicating that there are a total of 3 more poles than zeros. So we have 4 poles and 1 zero. The effect of the zero is hard to see directly. You don't see the slope level off. You don't see the phase bump up. And that's basically because it's so close to the other poles. So this 0 at s plus 3, its effect is hard to see because its break frequency is so close to these other poles. But overall, it appears that you have basically 3 more poles than zeros. In the same way that we could with the root locus, if you click on this data cursor, you can see the value of different points on the Bode magnitude and the Bode phase plot. So for example, if we wanted to see where the gain crossover frequency is, we wanted to see where the magnitude plot crosses 0 dBs, we could go along and we can see between 0.34 radians per second where the magnitude is positive decibels and 0.431 where the magnitude is negative decibels, the gain crossover frequency is somewhere in between those two. And again, we can change our selection style to mouse position by right-clicking, and then it'll interpolate a little bit. And we can try and find a magnitude that's closer to 0 decibels. And if we came down, we could try and find the corresponding phase at that frequency, so at a frequency of around 0.3. And we can get a sense of what the phase is and how close it is to minus 180 degrees. So it appears the phase margin is something in the neighborhood of 60 degrees or so, 63 degrees. We can also see the effect of adding a gain to our system. So we recalled that when we add a simple gain or change the loop gain to our Bode plot, it should shift the magnitude plot upwards, but it should keep the phase plot identically the same. So if we hold that Bode plot and we replot the Bode plot with an added gain of 10, use a different line type, we can see that the phase plots are exactly identical because the phase of a simple gain is 0 degrees at all frequencies. But we can see that the magnitude plot shifted up 20 decibels because 20 log of 10 is 20 dBs. And we can start to get a sense of what the gain margin is. how much gain can we add before our system goes unstable. Just for comparison's sake, let's open up another figure and plot the root locus of our open loop transfer function. So this is something that we saw before, but you could see that as we increase our gain, eventually some of the closed loop poles will move into the right half plane, causing the system to go unstable. And so it appears that right around a gain of 10, the root locus passes into the right half plane. So it looks like our system stays stable until we apply a gain, an additional loop gain of more than 10. So going back to our Bode diagram, this red line shows the magnitude plot when we've added a loop gain of 10 to our system. And so if we look at our new gain crossover frequency, it got pushed out to the right. And so our new gain crossover frequency is somewhere near here. It's near 0 dBs. And our phase at that frequency, you can see, is very close to minus 180 degrees. So here with our original system, the blue line, we had plenty of phase margin, 60 degrees of phase margin. When we increased K, we pushed the gain crossover frequency out to a point where we had less phase margin, and you can see we've basically put the system on the verge of instability. And this matches what was indicated from the root locus plot. Okay. Going back to our PowerPoint presentation, that brings us to the conclusion of this module. In this module, we learned how to use frequency response analysis to perform relative stability analysis. In particular, we showed how we can assess the stability of the closed loop system from the open loop frequency response. And we can do more than just assess absolute stability. We can get a sense of how robust the system is to instability, how close the system is to becoming unstable. And we learned two quantities, gain margin and phase margin, and the fact that both need to be positive in order for the system to be stable. We also demonstrated how frequency response can be used for system identification, for black box modeling, and we demonstrated that it's helpful for identifying higher order poles, faster poles than non-dominant poles, as well as zeros, which is an advantage to some of the techniques that we'd used previously.